Hello students, welcome to this new session, and definitely it's a pretty, of course, new. And why it's new? New class, new session, of course, and along with this, new for the first time, you're probably in your experience, first class between you and us will be done through an interface. We'll be not facing each other directly, but we'll be facing in a different way. So I hope this will be a more fun. So let us start with, once again, studies. So we'll start with a new chapter, that's states of matter. You may tell me, sir, it's a states of matter. Once again, we are reading this in class, in the previous class also. Definitely. States of matter, let me tell you a very interesting thing. States of matter, you will read not only in class 8, the states of matter you will once again, after class 8, some of the you will read once again in class 11, and 12 or some, and with high levels also. States of matter is that there is a chapter in the college levels also. So what's the difference? The content, of course. The content varies. Okay. States of matter. So I welcome you all once again, and let's start. With this, the name itself, as it says, states of matter. First, we need to understand two terms very carefully. What are the two terms? Matter and state. What is matter? Right? What is matter? Yes. What matter is anything. A very, very simple definition. Please first try to clear out the things from the basics. Before marking up, if you clear out your concepts, it will help you. It will definitely help you in the long way. So, first, matter, in simple definition, is anything which anything which can be felt by our senses. Senses means sense organs. So anything which can be felt by our sense organs, those are called matter. A simple definition about matter is anything which we want to rather elongate or elaborate onto this point. So what we will say that anything which we can see, feel, taste, touch, all these parameters, which if it satisfies, then all these parameter satisfaction, we will term that substance as matter. Example, anything. You can write chair, table, air, food, bag, shoes, dress, whatever your choice, you can give examples. And remember, once again, in class 8 you are now, so I'll request you, or definitely examples, every place, each and every definition needs to be accompanied by an example. Okay? Now coming to the next term, that's called the state. State means the physical form in which a substance is existing. A physical form in which a substance is existing. What are the physical, and those physical forms are having certain names. What are the names? Solid, liquid, and gas. So there are basically three major states of matter: the solid matter, liquid matter, and the gaseous matter. But are these three only states of matter? Only? Not more than that existing? Of course. More than that also exist. For your information, that's not this will definitely not come in your examination. That's for information. There's probably, and those students, I've told in the previous class also, that fourth state of matter, plasma, exists, and there are a total of 7 states of matter. So Just for information, there are total 7 states of matter. I've told you the fourth state. Fifth state is also there. It's a very low temperature and low pressure that it exists, called the BEC, and that's for information. So let's come back to that main topic. That is states of matter, 3 states of matter: the solid matter, liquid matter, and the gaseous matter. Okay. Now there is definitely, when we are talking about matter, it should have certain characteristics, right? It should have certain characteristics. What are those characteristics? It is made up of particles. Now, matter, what particle means? It is made up of something. Whether it's a solid, whether it's a liquid, whether it's a gas, it is made up of something. What are those something? We have termed as those things as particles. We have termed those things as particles. Now those particles, when they're existing, they will have space, interparticle space. It will have, because those particles are basically spherical in shape. Those particles are basically spherical in shape, and since they are spherical in shape, you know, the two spheres, when they touch each other, only a single point of the surface touches, right? If you want, you can take two different balls, and if you touch two different balls together, you will see only a certain portion, a very small portion, a certain point of very small portion of the two balls touch each other. The rest of the surface do not touch each other. So interparticle space has to be there, right? Those particles are in random motion. That means they're not at all stable at a particular place. That means, for example, you're sitting in a classroom and you're very much stable and sitting very quietly, not moving here and there. So that is called no motion state. But particles never ever stay in one particular place until and unless it's very compulsory. For example, in solids, the particles hardly move. But are they in totally rest position? No, they are not all in complete rest position. But they are showing minimum movement, right? Okay. Particles attract each other. Interparticle, when these particles they share a attractive force between each other. Every particle attracts the other particle. Every particle attracts the other particles. So a force of attraction exists between every particles. Now, based on this interparticle space, movement of the random motion of the particles, and the force of attraction, these properties of matter has led the foundation stone of a new theory called the kinetic theory of matter. And what are the prime features and the prime points of the kinetic theory of matter? That matter, similar as I said, that based on those features of a matter, that has led the foundation stone of what? The foundation stone of particles of matter. Foundation stone of the kinetic theory of matter. The kinetic theory of matter. Now, kinetic theory, the first is matter is made up of small particles. What's the second? Particles by which a matter is made up of. All the particles are identical in all respect. That means, for example, if you think, suppose, for example, you are sitting, so one particle of you, the entire class is filled with only one child. That means, suppose a class is containing 40 students, all the 40 students, one child. So it's not that all different children or different students are sitting together. No, it's not like that. But over here, all the particles are identical in all respect. Suppose if I'm taking a chalk So, and if I break it, or this chalk is made up of only chalk particles only. This chalk will not be made up of, or rather it's not made of wood particles, clubbed by chalk particles, clubbed by total cement. No, it's not like that. Not at all. Chalk is made up of chalk particles only. Right? Particles are having inter-particle space. As I said, two particles will be having certain space among each other. That's called the interparticle space. Force of attraction, I discussed earlier, the force of attraction exists between each and every particle. And particles are always in random motion. Kinetic, this word kinetic theory means the word kinetic comes from motion. And all the particles are in random motion. All the particles are in random motion. And interestingly, random motion particle, this random motion is not a very synchronized motion. It's not that all the particles are moving in a one particular direction and it will continue to move in one particular direction. That means, for example, there's a lane being fixed and the particles, some particles will move in, or rather will continue to move throughout their life. Lane 1, the other particles lane 2, some particles lane 3. No, it's not like that. There are no such roads, specified roads, pathways being mentioned or drawn over there. So what happens is they go for a zigzag motion. There is no specific pathway, no specific pattern over there. It's a totally messed up patterns. So it's a random zigzag haphazard motion which exists within matter. So such motion is what's called? There's a name, and it's called the Brownian motion. This name has been given after the discovery of this motion by the person. So Robert Brown was the person who discovered this feature which is existing among the particles of matter. Now let us discuss this solid, liquids and gases, the properties of solid, liquids and gases in terms of kinetic theory. We want to explain the properties. We want to demonstrate, or rather, we want to discuss the properties of solid, liquids, and gases, but using the concepts of kinetic theory. And this will definitely allow us to differentiate solids, liquids, and gases. Let's consider first one, shape. Solids, they are having a proper geometrical shape: square, rectangular, cubical, spherical, conical, cylindrical, triangular, trapezoidal. There are so many proper rhombic geometrical shapes that exist, and it only exists for solids. Why? Because in solids, if for giving this explanation that why it's having a shape, because for giving this explanation, we need to focus on 2 points given probably if you focus on these 2 points, interparticle space and interparticle force of attraction. Based on these 2 points, the answers will be given. That why the solids are having shape, fixed, proper geometrical shape. That why it's having? Because the interparticle space and interparticle force of attraction, interparticle space and interparticle force of attraction within solids are maximum. And for this reason, since they are, for this minimum interparticle space means all the molecules are very tightly packed together. Minimum intermolecular space means all the particles are tightly packed together. And since they're tightly packed together, that packaging, due to minimum interparticle space, which leading to the development of the maximum interparticle force of attraction, and followed by a very good packing structure, packing system, or rather packing of particles existing, that is giving the shape to solids. What's the problem with the liquids? Liquids, this interparticle space is quite more compared to solids, and thus, since the interparticle space is more, the interparticle force of attraction also decreases, and thus the efficiency of packing of particles, that means how well that has been packed together, that efficiency decreases, and hence so liquids fail to undertake a proper shape. But since it's slightly more, it's more than it's not the maximum, but more than solids, for that reason, liquids take up the shape of the container in which it is being kept. So it's possible to view a liquid in a proper shape, because whatever the shape of the container will be, that will be the shape of the liquids. Coming to gases. In gases, the interparticle space is maximum and interparticle force of attraction is minimum. Since the space is maximum, that results to the decrease in the interparticle space, and thus, interparticle force of attraction, decrease in interparticle force of attraction. And since these two, maximum space, minimum force of attraction, the packing efficiency, that means the packing of the particles, it drastically drops. And hence, under such a condition, it becomes very, very difficult for a state of matter to undertake a shape. But there is an advantage. What is the advantage? Such a situation has given rise to a power, to a property, to the liquids as well as to the gases. That they are having that property, they developed the property, because they've compromised on one point. And what's the property? That's called the ability to flow. So liquids and gases, which can be also termed as fluids under one banner, fluids. Now such a condition, fluids, so they are gases and liquids, they're mobile, they're fluid, they can flow from one place to another place, okay, on its own. And since they can flow, and since they can take up the shape of the container in which it is kept. For the liquids, it can be seen visually. For gases, it becomes difficult until and unless the gas is a colored one. This lack of packaging of particles, but rather poor packaging of particles in liquids, in gases, very, very poor, that has allowed the gases to flow, that has also allowed the gases to be compressible. Minimum interparticle space or less interparticle space, less interparticle force of attraction, minimum interparticle force of attraction under maximum interparticle space, minimum interparticle force of attraction, medium interparticle space, and medium interparticle force of attraction. Such a condition, fluids or the states of matter becomes compressible, because only those substances can be compressed which are having interparticle space left. That means such amount of space exists where if the external force is being applied, there is a space enough for the molecules or the particles to move and to take up that one space. Okay? And such packaging has led to hardness. So solids are very hard. Why? Because maximum interparticle force of attraction and minimum interparticle space, packing efficiency is very high, and thus they are very hard and rigid. And since the solids are having interparticle space minimum and maximum interparticle force of attraction, thus the volume decreases, because volume is dependent upon the what should I say? Volume depends on the interparticle space. So any substances or any substances whose interparticle space is more, definitely their volume will be more. Now coming to the next, probably you have already read this one in the previous class, that is interconversion of states of matter. That means conversion of one state of matter into another, and once again returning back to the same original state. That's called interconversion. It's not only conversion. If only one step is being taking place, that is from solid to liquid to gases, that's basically only conversion. But when I'm saying or discussing the word interconversion, that means from one state of matter, from solids to liquid to gases, again gas to liquid to gas, or solid to liquid to gas, solid to liquid to solid, liquid to gas, and gas to liquid back. This cyclic process has to be there. Interconversion of states of matter include this cyclic process. Cyclic process has to be there. Interconversion of states of matter. Now, this interconversion of states of matter that means from solid to liquid, liquid to gas. This conversion is being controlled, this conversion is being controlled by temperature and pressure. So external temperature, external pressure, by these two parameters, this interconvertibility, or from one state to another state, this interconvertibility can be changed, that means can be controlled. If one substance do not want, or rather do by its own from one state to another state, I can bring them back. I want, suppose for example, if I keep ice, if I have taken ice and I keep outside, the ice will melt. So solid to liquid, am I doing anything? No, that's natural. So ice to water, that's natural. So I'm not doing anything, external heat and surroundings, so that's natural. But if I want that ice back, I have to do something. That is from outside, external pressure, temperature. I have to change certain parameters, either one or two, for bringing that water back to ice again. So their temperature and pressure do change, do alter, or do control the interconvertibility of states of matter. The example given, water, liquid water and heating forms water vapor. And if I cool this one, once again, cool the water vapor, I'll get the liquid water back. Water liquid and cooling forms ice, and ice on heating forms water again. Cooking cylinders, LPG. Probably you've noticed that if you switch on the gas, that nozzle, what it comes out? Gas. You can smell the gas. But inside the cylinders, what it contains? Gas. No. The gas is being basically over there gets converted, or rather is being converted into liquid state. The gas, so over there, the gas is being kept under high pressure. And by the application of pressure, that gas, the cooking gas, is inside the cylinders is being converted into liquid state. And for that reason, within such small cylinder, a huge amount of or volume of gas can be stored, rather it gets stored. Okay? That's called a liquefied petroleum gas. High pressure inside the cylinder, low pressure outside the cylinder. So from high pressure to low pressure, when the pressure is released, the liquid instantly gets converted into the gaseous state. Water cycle, interconversion of states of matter. Ice to liquid water to water vapor. Water vapor again gets converted into, after condensation, or rather after cooling, gets converted to liquid water, which finally once again to ice. It goes on the surface, upward in the clouds, followed by the mountains regions, ice, It's a cyclic process goes on. Some of the ice melts from rivers down to the seas and oceans. Cyclic process goes on. Ice skating. Probably you will read this explanation in the physics chapter, that ice skating, how ice is not having a very smooth surface, a rough surface, but when it's when a person who is using the skates, they easily slips from one point to another point, and the wheels through that easily roll over there. What's the reason? When a person or any that's ice skating that sport goes on, a person when they use this person's skates, there's the wheels which are available over there on that particular point on the wheels. A huge amount of pressure is applied. Because applied means I'm applied. Basically, when I'm standing on those wheels, my entire body mass gets concentrated on the tip of those wheels, and when it rolls, my body mass always gets concentrated on the tip, and for that reason, the ice which remains over there under that point gets converted into liquid. So under intense pressure, ice gets converted into liquid, and the moment that pressure gets released, the water instantly becomes ice again, because the surrounding temperature does not allow that liquid water to be in the liquid state. But under extreme pressure, that ice gets converted into liquid, and for this reason, the ice skating smoothly goes on. Now I've given you a question: why Earth's inner core is solid? Find it out. Do you know that why the Earth's inner core is solid? Interestingly, the surrounding temperature of the inner core is around 6,000 degrees Celsius. Whereas inner core and the outer core, it mainly contains iron and nickel, and at such temperatures, all the elements gets converted into vapor state. If you check out the melting point and the boiling point of iron, nickel, and all the elements what you're having on Earth, at such temperature, all elements are having their melting point or the boiling points above 5,000 or 5,500, above 6,000. Gets converted into the gaseous state. But what happens, or why Earth's inner core is solid? Find it out. That's a homework given to you. So with this, I'll take a break for now. I'll stop over here in my first class. I'll continue with this chapter in my next lecture, in the next class. Thank you, students, and this situation is very serious, so the message given: stay at home and take a very good care of yourself. Thank you.